Okay, so we continue with quantum theory, which we started in the second half of the last week lecture. So the title is a quantum Teichmüller theory. And actually, last time we didn't talk about Teichmüller theory at all because we discussed the general principle of quantization, which consisted of two steps. First step was purely algebraic, and which corresponds more or less to deformation quantization, which means that it is on the general grounds well-established part. And the second part is more interesting part, which deals with the realization of formal algebra in Hilbert space and construction of operators realizing symplectomorphisms. And today we start to realizing the basic algebraic system of the Teichmüller theory in quantum theory. So our goal is to quantize the basic algebraic system V R W, where V is a square of the first quadrant, first positive quadrant. R is a map from V to V, which we already wrote many times. So the couple of positive numbers goes to 1 over x2, x1, 1 over x2. And the third element is W, which maps V squared to itself, and which associates to a couple of pairs of positive numbers, another couple of pairs of positive numbers, which we denoted x dot y and x star y. And I will not write the formula. You know it by now. And I will not write it today, at least, because I don't think that we will go that far to work with this part. We will work with this part. And we have a symplectic structure. So this is an additional ingredient, which is crucial for quantization, and the symplectic structure. Symplectic structure in V, given by the two-form, most simple two-form you can imagine, which which is a canonical two-form in R2 in terms of logarithmic coordinates. And so today's goal is to start working with a part of the simplest part given by two first items in the triple. Quantization of V R omega V. So despite this is a very simple part of the story, and as a consequence not very interesting, but I will spend today's lecture on that simply to highlight most ingredient things, because the principles we will be using to arrive to quantize R will be of general nature, and this is why we will discuss them in detail. So first we remark, of course, that here the logarithmic coordinates are important. So in logarithmic coordinates, xi equal e to xi. So the V, the space V is equivalent with R2 with canonical symplectic form. So omega V becomes a d capital X2 wedge d capital X1. So in this case we discussed last time already. And so the step one consists in choosing an algebra. But we will keep this relation between the logarithmic coordinates and the original coordinates as a main guiding principle of guessing or getting right formulas. So, for example, we start by definition. So we associate to V an algebra V sub h bar given by presentation. So V h bar is a complex algebra generated by two generators, x1 hat, x2 hat, subject to one relation, x1 hat, x2 hat, equal e power I h bar, x2 hat, x1 hat. Okay, but the remark is the following. So how we get this definition? There will be many remarks today. So I decided to start enumerating them. So there will be two numbers. First number is the number of the lecture, and the second will be number of remark. Okay, so today is 7th lecture, if I count it right, and the first remark. So this definition comes. This definition is natural in terms of natural because of logarithmic coordinates. And why it is so? Because if we start with logarithmic coordinates instead of little xi's, then we have a canonical symplectic form, and then we discussed the canonical quantization of it, which was complex algebra x1 hat, x2 hat, with a Heisenberg commutation relation, which was x1 hat, x2 hat minus x2 hat, x1 hat equal I h bar. Right? So that was a canonical quantization of R2 with that form. We verified the conditions which imposed on the first step. And now we are dealing with exponentials, and this is an easy exercise to get this relation if we use the substitution. So if we take xi equal e to xi with hats, then and apply Baker-Campbell-Hausdorff formula, then with Baker-Campbell-Hausdorff formula, we have what we have: x1, x2 hat equal e to x1 hat e to x2 hat. So which is e to, so Baker-Campbell-Hausdorff, x1 hat plus x2 hat plus 1/2 x1 hat x2 hat plus so on. And then we use this. So we get x1 hat plus x2 hat plus I h bar half. But if we do it in opposite order, so the same calculation. So the only thing that if we exchange 1, 2, it corresponds to changing the sign of h bar. So this becomes e x1 hat plus x2 hat minus I h bar. And now comparing two formulas, we get x1, x2 hat equal e to I h bar x2 hat x1 hat. And but this is kind of heuristic because exponentials are formal things. But there will be a second step where everything will become non-formal. It will define the exponentials of quantum mechanical operators. But at this stage, this remains formal. And then we just take this as a definition of the starting algebra. And so this principle of referring to logarithmic variables to get formulas for non-logarithmic variables will be basic principle we will be following in the rest. Okay, so now if we look at the quantization procedure, so this is R. We have a symplectic morphism R, which we want to quantize. So quantization of R. And the general formula tells us what? So if in logarithmic coordinates R star x1, x2. So what is it? Here is a formula. So we take the logarithmic coordinates. It will be minus x2, x1 minus x2. And then just not to get me to be mistaken with signs. So we denoted the quantization, the automorphism of the algebra, of the quantum algebra VH, parentheses with subindex h bar, and we put r minus 1. So this should act on x1, x2 hat, and should give so that's our choice to put here hats without any changing. But we profit of linearity of the system to guess that formula. That's a definition. This is definition, or in our in other terms, our choice. this is classical thing, and one of the principles of quantization is that in the limit, when h bar goes to 0, this formula should become this one. And so this part is evident. You just erase the heads. Okay, now let us apply our principle of guessing the formulas for little x's by using this. So then what we have r minus 1 h bar acting on a little x1 hat, x2 hat becomes e to minus x2 hat, e x1 hat minus x2 hat. And now we want to rewrite it in terms of little xi's. We want to forget about the capital X's. So the first one is OK. So it's just x2 hat inverse. But the second one is not OK because we have to split x1, x2, which are not commuting. So we have to refer to Baker-Hausdorff-Campbell or Baker-Campbell-Hausdorff. To write it as a e x1 hat e minus x2 hat, and we have to correct by the inverse operation over there. So we have to put minus 1/2 x1 hat, commutate the x1 hat with minus x2 hat. In principle, there is an infinite series, but because of our algebra, this infinite series truncates to the very first term. So this becomes what? x2 inverse, x1 hat, x2 hat inverse. And this is 2 minuses disappear. This becomes I h bar. So it's e I h bar half. Or the same thing, x2 hat minus 1. We can now exchange two x's to get x2 hat minus 1, x1 hat. And the x1, x2 commutes with I h bar. Now when we put the inverse here, we put the minus over there. So minus I h bar plus half of I h bar, so it becomes e minus I h bar half. Okay, so that's this. We take underlined part as definition of R sub h bar acting on V sub h bar. Okay, so that's the result of applying our principle. So we didn't guess this. We started from here, arrived to here, and forgot about what we used. And we give this a definition. And here is a fine feature of quantization. As you see, when things become non-commutative, sometimes formulas are not that evident as they look from classical part. So here, due to linearity, no such feature. And here, we have a multiplicative operation. So we corrected it by Planck constant. So when h bar 0, we get back to classical formula. But here, the context is very simple, so it's not big deal. But anyway, you see that on quantization process, ordering of operators somehow important. Okay, now we finished the first step of the quantization, and we are getting to to the second step. But before starting the second step, I'd like to make a remark on Heisenberg operators. Are there questions up to now? Okay, the remark 7.2. So we from now on we will be using the normalized momentum operator in L2 of R. So what I mean here, so the p hat, the momentum operator acting on the Dirac-Bra vector from the right is the same thing as 1 over 2 pi I d over dx x. So if you compare the formula we used in the first lecture, maybe, so this p normalized is 1 over 2 pi h bar p non-normalized. This is the old p which we used, and this is a new p which we'll be using from now. And why we use we will be using this? So the advantage of this choice is because of the formulae. F q hat f minus 1 is p hat, and f p hat f minus 1 is minus q hat, where f is a Fourier operator, unitary of L2 of R, the Fourier operator of Fourier transformation. X f y is defined by its integral kernel, which is e 2 pi I x y. Okay, so if you come back to old p, then we have to we would put it here 2 pi h bar, and you see, so the formula looks more ugly than now because of presence of 2 pi h bar. So this dictates this natural normalization. Okay, now we turn to step 2. In my notes, I missed one remark, but never mind. It will be exercise. Okay, so okay, let us leave it as here. So step 2. Yeah, maybe I'll make it anyway. So remark 7, 3. So we have the property R H bar power 3 is the identity of V H bar, and this will be exercise. Simple exercise of applying 3 times this transformation, and then R H bar will be the square of R minus 1 H bar, which is explicit here, and the formula will be x2 hat. Formula is e to I h bar half x1 minus 1 hat x2 hat x1 hat minus 1. So never mind. So this is 7.2, this is 7.3. So that's what I missed as a remark. And then here we should add Q hat, P hat, or P hat, Q hat equal 1 over 2 pi I. That's a Heisenberg commutation relation, which we'll be using from now on. Okay, so finally we can turn to step 2 of quantization. So we have to pick up a Hilbert space. So we choose or the I don't know, Hilbert space H sub V. So V refers to our V R squared. Positive, which will be L2 of R, Hilbert space, and the realization. X1 hat is equal E 2 pi B Q hat, and X2 hat equal E 2 pi B P hat. Now QP are those QP. Q is a multiplication operator, which was defined in the very beginning. P is a new normalized momentum operator. They are self-adjoint operators in the L2. Now these are true exponentials in functional analytic sense. So these are self-adjoint. You have spectral theorem, but this is diagonal. So X1 is diagonal, which multiplies. So let me write it once for any f in L2 of R, or maybe the domain for any f in the domain of X1 hat sitting in L2 of R, x1 hat acting on f of x is e 2 pi b x f of x. And the x2 hat is equal conjugation by Fourier of x1 hat. Because of that formula. If we, so you see, if we continue this, f e 2 pi b q f minus, so this is a Hermitian conjugate, but f is unitary, so Hermitian conjugate is the same as the inverse. And now if we write it this, we can put it like this. Right? So we can insert it into argument like this. On the level of polynomials, it's algebraic exercise, but here, this is definition. Right? We define it like this, and then we use our formula, so we end up 2 pi b hat. So, so as soon as we define this part in a functional theoretical way, so we don't discuss what its domain, but you can see that its domain should be such vectors, b will be positive real, decaying sufficiently rapidly at plus infinity. Right? But I am not going to spend time on discussing these issues. It's always, you can restore all that kind of information without any problem. And and the second part defines x2 in terms of x1, so no problem. These two operators are well defined now operators, and the remark is that remark 7.4. So x1 hat, x2 hat are now self-adjoint operators with a non-negative spectrum. Non-negative spectrum. Spectrum of x1 hat is equal to spectrum of x2 hat equal positive half axis. Why it is so? Because the spectrum of Q is a whole real line, and now we see that the exponential takes exactly the whole positive part of the real axis. But why we put the equality here? Does everybody know why? Why it is not strict inequality? Why we include 0, even if this never vanishes? Nobody knows? Because the spectrum is by definition a closed subset of the complex plane. Right? So we have to add this a limit point. Always a closed subset. Any spectrum. And furthermore, x3, which is here, x3 e to I h bar half, x1, let me, maybe we should write a formula first for relating. And so we fix B as a positive solution of the equation h bar equal 2 pi b squared. So saying differently, it's the square root of h bar over 2 pi. But why it is so? Because if we try to calculate, here's the explanation. So if we take now, do the same exercise as we did before with Campbell-Baker-Hausdorff, which still works here. So we end up with 2 pi b q hat, 2 pi b p hat, commutator x2 hat, x1 hat. And now this commutator becomes 2 pi squared b squared times commutator of q and p, which is I over 2 pi. Because of here. So 1 2 pi goes away, and the rest becomes 2 pi b squared I. And that's why we have to identify this with h bar. Okay, this is a parameterization, and this is our choice because we cleared up p and q from h bar. But h bar should find itself somewhere, and it finds, we put it in symmetric way, and you will see why we need this symmetric way of doing it. But already we will see it in a moment, that furthermore, x3 hat given by I h bar half, x1 hat inverse x2 hat is also self-adjoint with spectrum positive half line. And this is, looks counterintuitive. So x1 is positive, x2 is positive, is multiplied by pure phase, and x3 stays positive. Right? This looks strange. So how multiplying positive things by a complex number, we still get a real positive thing. But in operator theory, things are like that. So nevertheless, if you write it explicitly using a Baker-Campbell-Hausdorff for the exponentials, x3 becomes a e 2 pi b, x2 is a p hat minus q hat. Right? Because of putting p and q simultaneously in one exponential removes this complex contribution because of non-commutative nature of p and q. And now this is a simple thing because it is conjugated to to x1 or x2, namely, we can put it e pi I q squared e 2 pi b p e pi I minus pi I q squared. E pi I q squared. This is a unitary operator because of this I, right? And this is in the middle is x2. And why we have this? Why we have this? And this is just story of, again, Baker, Campbell, Hausdorff. So that's the answer for the question mark. Pi I q squared p hat e minus pi I q squared. What is this? This is p plus commutator pi I q squared with p, and so on, infinite exponential series of commutators. And now if we calculate, it will be derivative of that with respect to q, pi I q hat, times commutator of q hat and p hat. And again, twice, so that twice. And using the commutation relation over here, so we get p hat minus q hat. Right, exactly. But of course, by definition, we put this conjugation into the as argument of the exponential, and use this argument. And then we explain this equality. So you see that x3, despite the fact that formally it looks strange and complex, x3 hat becomes eventually the conjugation, unitary conjugation of a positive self-adjoint operator, which means that itself x3 also is a positive self-adjoint. Okay, now we have explained everything as concerns the algebra, realization of the algebra in Hilbert space. And the last thing of the second step is calculation of the unitary operator R hat, a quantum realization of the symplectomorphism. Hat. And so the equation to solve is as follows. So if you look at the general principles, so then the conjugation of xi hats, the generators of our algebra, should be the image of xi hats under the algebra automorphism, which we defined in the first step. And yeah, I think we stop here to continue after the break. So, but basically, it is a linear system for R, homogeneous linear equation for R, which means that a priori, for a priori reasons, because of the theory of homogeneous linear systems, there is not unique solution. There is a space of solution, a vector space of solutions. But the difficulty here is that it is an infinite linear system in an infinite dimensional vector space. But general argument is like in a finite dimensions, so vector space of solutions. And we will see how we solve it just by using basically Baker-Campbell-Hausdorff. Okay, so this system of equations is equivalent to capital Xi hat inverse Xi. So due to linearity in terms of capital Xi's, here Xi small u by Xi hat is equivalent to R so Q hat R hat minus 1 should be equal to the image of X1 hat by this automorphism. And if you look at the formula which was written before, it should be equal logarithm of x3. And x3, as you see, it's 2 pi b, same multiplicative constant, so p minus q hat. Okay, this is I equal 1, and r hat p hat minus 1 will be equal inverse of x1 minus q I equal 2. Okay, that's a linear system to solve. This is equations for R, so that will be notation. And what else? So what we can say here is the following. So we can put together these two equations in this form. So this is not a scale product, just a two-component operator. So it should be this action component wise. So we just put together two equations. So the image of p hat is minus q hat, comma image of q hat, p hat minus q hat. And now this is a linear transformation, so we can write it as a row vector pq multiplied by 2 by 2 matrix. And what is this 2 by 2 matrix? Is 0 minus 1 and 1 minus 1. So this is the element of SL to Z, which sits in SL to R. And so the R hat is an element of quantum realization of the metaplectic group. Group G sitting in unitaries of L2 of R, generated by by Fourier operator and the family of exponentials I, T, Q hat for T in R. That's we discussed, I think, in lecture 2 about metaplectic group, and it was defined exactly this way. So any transformation by a unitary gives a linear transformation between P and Q. That's a general definition, and we have a particular case of that given by that matrix with ones and minus ones. So, so the solution now exists just by the fact that this matrix is indeed of determinant 1, real matrix of determinant 1. And the general statement about the metaplectic group tells us that for any 2 by 2 real matrix of determinant 1, there is a unitary operator which solves this. So on the level of solution, existence of solution, it is just here. And the only thing remains to do is to find that solution. Okay? But as you know, existence not always is sufficient to find out the solution. We know the Brouwer fixed point theorem, right, which tells that any continuous map of a closed ball to itself has a fixed point. But to find the fixed point in practice is very different to just knowing that existence. This is not quite the same thing, so we will find now step by step this matrix R by explicit terms, and we will write it in terms of the generating elements. But before doing so, let me just, yeah, so this is remark 7.5. We start from preparation work, and it consists of 2 lemmas, which are not difficult lemmas. And indirectly, we already addressed those lemmas in the quantum part, in the first part of the course. And we just see those statements in different light in terms of Heisenberg algebra of P and Q operators. So as a preparation to find, to solve equations for R, we start with 2 lemmas. So lemma 1 or 7.1, which tells the following. So let A be an operator commuting with Q. Then there exists a function. Okay, let me put it measurable, almost everywhere defined. But this is in parentheses. Usually we omit all these works. We just say there exists a function f from real line to C such that A is equal f of Q. Saying differently, any operator commuting with q hat is a function of q hat. And the proof is easy. We just use the integral kernel. So we have a q equal qa is equivalent to x a y y equal x x a y. So in terms of integral kernel, this is equivalent to x minus y x a y equals 0, and this is equivalent to, so you see, if x not equal to y, the integral kernel vanishes. So it doesn't vanish only for x equal y, but integral kernel is a distribution. So we have to solve it in the space of distributions, and this just means that x a y is some function f of x, or delta function of x minus y times some function of y. So you see, if you multiply by x minus y this thing, we know that in the distributional world, x minus y, x delta of x is 0. And this is the function which I assume is of this kind. So that's a general solution of that equation. But it can be even delta function of y, right? So it doesn't contradict, because anyway, this is a even more extended statement. But for us, it will be sufficient to work with just usual functions. And now this is equivalent to the fact that A is f of q, right? The end of the proof. But as I said, we did this lemma in the context when we proved the irreducibility of the Heisenberg-Weyl representation of the Heisenberg group. But let me put the immediate corollary. So if we have an operator which commutes with P, then it means that A is a function of P. A equal f of P for some f, let me put it this way, C power R. Because it suffices to conjugate by the Fourier operator, and then we are to the lemma. So no difference. And now the lemma 2, 7.2, says that let fg in two functions, C power R, be such that f of q equal f of p, g of p. I assume that we have two functions, and one function with the argument operator q, another one with argument operator 2, and they are the same operators. Then f equal g equal constant. So this equality implies that these functions are just constant functions. Proof again uses the integral kernels, but first what we should say, what is g of p? So f of q hat equal g of p hat.
is the same as f of q hat equal conjugation by the Fourier operator g of q hat. And then we switch to delta function, to integral kernels. So x minus y, f of y is equal, so let me put it this way. So x f t g of t t f minus 1 y dt, right? So I use the multiplication of the operators by inserting the decomposition of unity in the middle, and this is equal to g of t e to 2 pi I t x minus y dt, and so this is g tilde of x minus y, where g tilde is the Fourier transform of the function g. So what we have, delta function of x minus y times of f of y is equal g tilde of x minus y. So now we can translate x by y, delta of x, f of y equal g tilde of x. And now you see that right hand side does not depend on y, so should be the left hand side. So this means that f of y is a constant, and g tilde of x is c times delta of x. And now it remains to calculate. We already arrived to the conclusion that f is a constant function. But to see that the function g is constant, we have to make an inverse Fourier transform. So g of x is equal integral g tilde of t e 2 pi I tx dt. So inverse Fourier transform. We insert this c delta of t, so the integral easily is performed equals c. So you see that the function g itself is the same constant. So we put as a remark that these things we did already indirectly 7.6. So the lemmas 1 and 2 imply irreducibility of the Heisenberg-Weil representation of the Heisenberg group. Something what we did already, but we used the exponential unitary operators there. And here we didn't use exponential operators, just Heisenberg operators P and Q. And so these two lemmas is an alternative way of proving proving the say reducibility theorem. But anyway, it's good to have to know to prove one and the same statement in different terms. And now finally we turn to solving our linear system in R. And let me just start from the answer theorem, the only theorem of today. So any solution of ER satisfying the normalization condition R hat power 3 equal 1. So 1 means always identity of L2 of R. Is of the form R hat equal zeta E 3 pi I Q hat E pi I P hat minus Q hat squared, where zeta is a complex number satisfying equation zeta power 3 is equal minus 1. So saying differently, with this normalization, there are only 3 solutions. And let us see how this is proven. So I recall that ER is the following. R hat conjugates, what was it? Okay, let me put it together. P hat Q hat was equal minus Q, P minus Q. So let us start from first equation, equal minus Q hat. So this is the same as R hat P hat. R hat equal Fourier conjugates P hat. But if you look at the Fourier operator, then the conjugation of P by F gives exactly minus Q. And this is equivalent, we put together Fourier, inverse Fourier times R hat, P hat, R hat times Fourier is equal P. So we see that R times R inverse, F inverse times R commutes with P. So this is equivalent by lemma 7.1 that F minus 1 R hat equal F of P hat for some F in C power R. Okay, so that's
there should be R inverse in the equation.
yes, thank you. And here also, and here also. And then the second equation So r hat, q hat, r hat inverse, which is p hat minus q hat. So let us equate this with Fourier conjugation with Fourier. So Fourier, something Fourier inverse. So we get P by conjugating by Fourier of what? Of Q, right? I'm checking my notes just to avoid unnecessary extra calculation. Yeah. So if we apply conjugate Q by F, we get P, this term. And likewise, what we have to put here, P, because minus Q, as we just used it here, is obtained by conjugating P by F. Okay, so this is equivalent to F minus 1 R hat, Q hat R minus 1 F equal P plus Q. And now we realize this as also a conjugation of Q by pi I over of P squared E minus pi I over P squared. Because by Baker-Campbell-Hausdorff, what we have is Q hat plus pi I P hat squared Q hat commutator, and no other commutator because it's commuting. And if we calculate the derivative with respect to P, 2 pi I P times commutator of PQ, which is the inverse of 2 pi I, it cancels, so we get back to here. Okay, so we have this, and we put everything together. So this is the equivalent to say that E minus pi I P squared F minus 1 R hat Q hat R minus 1 F E pi I P squared equal Q. Again, we got some operator which commutes with Q. And by lemma, still lemma 7.1, we conclude that E minus pi I P squared F minus 1 R is a function of P hat, Q hat. It commutes with Q, so it's a function of Q hat. But this is, what is this? By previous thing, this is F of P. So altogether, this is a function of P equal some other function of Q. So by lemma 2 now, we conclude that g of x equal E minus pi I x squared f of x is C. And thus, we solve for R, becomes so E minus pi I P squared f minus 1 r. No, this is not reals, but operator r is equal c. And this we can easily solve for r, which is inverse of this. C times f e pi I p squared. So we, without normalization condition, R is just a multiple of a fixed operator. So the solution space of our linear homogeneous system is one-dimensional. But now we know how f behaves with respect to p, so we can exchange the two things. So we can write another version of the formula. So conjugating by f of p by f converts it to q, and we put f on the other side. Okay, that's our formula, most compact formula, I think, for R. And now the normalization condition. So R hat cube should be 1, right? One unit operator. So let us do that. So we have equal c power 3 e pi I q hat squared f 3 times pi I q hat squared f e pi I q squared hat f. And now we let us move all f's to the right, because we know how to conjugate things. C cube e pi I q hat squared e pi I p hat squared. So this is just playing between these two versions. Here we move this f to the other side, q becomes p, and f squared pi I q squared f. And now we have to push 2 copies of f through this exponential. So first f converts q to p, second f converts p to minus q, but minus q squared is a q squared. So this commutes with it, so it passes freely to the other side. E pi I p squared e pi I p squared, no, q squared, f cube, f cube. And now I have to refer to one exercise which you did some time ago, namely exercise 2 of series 2. So by exercise 2 of series 2, e pi I q hat squared e pi I p hat squared e pi I q hat squared is equal, and the phase factor was wrong in the exercise, as H.E. told me at the time. And this is equal e pi I over 4f. Right? While in the exercise it was put minus here. And so you know how to do that, right? So to check this. So we take it for granted here. And now if we substitute this, then we can finish the calculation like c cube e pi I over 4 f4. But f4 is 1. Fourier transform is always of order 1. So it's c cube e pi I over 4. So this is the equation for C. So you see that this 1 should be equal to C cubed. Of course, we can determine C up to third roots of 1, which is not very illuminating, because in the theorem, the root is much simpler, just the third root of -1. There is no any phase factors like pi over 4. So what we do to remove this pi over 4, we do the following. So we just rewrite our formula, trying to bring it into that form. So we write r hat equal C e pi I q squared f. And now we use this. If we use this, what we get, the CE, this 2 pi I q squared, here is one more pi I q squared, 2 pi I q squared e pi I p squared, e pi I q hat squared. And now we we move this q hat to the other. So I lost phase factor. So we replace, so this should be E minus pi I over 4. And the rest is correct. And now we put a C E minus pi I over 4. E 3 pi I q squared, E pi I. And then we have to conjugate P with inverse of this. And this is the story of Baker, Campbell, Hausdorff. So this is a P hat minus Q hat squared. And now you see that this is equal. So the consequence of that is that zeta is given by C times E minus pi I over 4. So now we raise zeta to power power 3 equals C cube E minus 3 pi I over 3 over 4. And by this equation, C cube is the inverse of E pi I over 4, E minus pi I over 4 minus 3 pi I over 4, and that minus 1. So that's the end of the proof. And that's the end of the quantization part of the simple piece of the basic algebraic system. Maybe maybe it's just a remark, which doesn't concern what we are doing here, but concerns this underlying formula. Formula star. So the formula star implies that e to pi I q squared e pi I p hat squared e pi I q squared equal e pi I p hat squared e pi I q hat squared e pi I p hat squared And all this is equal to e pi I over 4f. So the first left-hand side is just this equality. But right-hand side, what is it? I just conjugate this equality by f. F commutes with f, so the right-hand side doesn't change. But if we conjugate term by term here, then q becomes p, p becomes q. And this is an equation which is a form of the spatial case of the Yang-Baxter equation. In infinite dimensions. Usually, we talk about R matrices in the context of finite dimensional vector spaces. And here we have an example of solution in infinite dimension, in Hilbert space of square integral functions. But usually we write a Yang-Baxter equation in this form: R12, R23, R12, R23, R12, R23 with the tensor components. And we can write it exactly this way by realizing Q to be P1 plus Q2 and P to be P2 plus Q3. But if we put now ourselves to a context of a Hilbert space of L2 of R3 in L2 of R3. So we have 3 pairs of PQ operators. And then you see that Q hat, P hat. The only thing which matters here is the algebra of Heisenberg commutation relation. So if we check commutator of PQ, then this is P1 hat plus Q2 hat, P2 hat plus Q3 hat. So P1 commutes with everything, which can be dropped. Q3 commutes with everything because there are no 3 over there. So this is Q2 P2. And Q2 P2 is the same as QP is I over 2 pi. So these substitutions doesn't spoil the algebra which underlies the identity. And but now Rij here is given by E pi I Q P pi or maybe Jk Pj plus Qk squared. So we have, as you see, literally we have R matrices given by unitary operators in L2 of R. And one can show, this is after all the quantum topology, right? One can show that this R matrix gives rise to not invariant of the form of the form invariant of a knot is 1 over determinant of the knot times phi of k. So determinant is a determinant. Alexander polynomial as a delta of -1, or the order of the homology group of the double cyclic covering of the complement of the knot. But this is a long story, but eventually it you can write the finite dimensional version of that R matrix, and in that finite dimensional version, this is an old paper of Vaughan Jones and somebody else on what they call metaplectic knot invariance. So metaplectic in the finite dimensional context, but we have an infinite dimensional version of that metaplectic construction. And the machinery we are using here, functional analytic, is something which was missing in Jones' viscous paper, because they were dealing on the finite dimensional. But in an infinite dimensional case, you can still push all the way to get that far, as a knot invariance. But this we will not discuss here, because our goal is Teichmüller. Okay, I stop here and see you next week.